morning, good afternoon, good evening. Thank you for joining us today. My name is Brent Berenson, and I will be the moderator for our presentation today. I'm the leader of Fluor's Business Transformation and Innovation team. We focus on new and innovative ideas, never losing sight of the critical thinking and analysis that comes from our global team of experts. Our people are the core of our success. This webinar series is an opportunity to showcase specific expertise, to talk about new trends or recent code changes of significant impact to our industry. As with other webinars, this will be a technical presentation. Subject matter experts Sanjiv, Dabee, and Katie Johnson will talk about gasification and exciting technology consideration in the transition to renewable energy. Sanjiv and Katie will discuss how biomass gasification can meet a growing need for waste utilization, various aspects of the technology, and additional considerations in the development of a biomass gasification plant. We have two subject matter experts with us this morning. First, we have Sanjiv Dabee. Sanjiv is a Fluor Fellow with expertise in gasification and syngas. Sanjiv has over 25 years of industry experience, which includes syngas generation, syngas processing, and syngas conversion, biomass to liquid, coal to liquid, gas to liquid. His expertise includes licensor evaluation, conceptual design, detailed design, construction, commissioning, startups, and troubleshooting. In his spare time, Sanjiv is an avid hiker and enjoys snorkeling at the local beaches. A fun fact about him is that he's lived in 3 different countries and traveled to 24 and counting. Joining Sanjiv is Katie Johnson. Katie has 5 years of experience with Fluor, working on projects involving biomass gasification, syngas processing, natural gas reforming, chemicals production, and hydrogen production. Katie's experience includes technology evaluations, technical studies, and conceptual and preliminary design. Outside of work, Katie enjoys traveling, the mountains, and visiting the beach in sunny California. Before we get to the main presentation, Fluor has a very strong safety-driven culture, and as such, it is customary for us to start our meetings with a brief safety topic. With that, I would like to ask Katie to please unmute her line and begin with the safety topic.
Thank you, Brent. For our safety topic today, I want to share a few considerations for safe biomass handling. The biggest safety concern is that biomass presents a significant fire hazard. For those who are familiar with the fire triangle, the 3 elements required for a fire are fuel, an oxidant, and heat. In biomass handling, the fuel is the biomass, the oxidant is the air, and the heat can come from sunlight, moving machinery like conveyors or grinders, or sometimes, in the case of self-ignition, the biomass itself. Only 2 more elements, dust dispersion and confinement, are needed to move from the risk of fire to explosion, and both can be present with biomass storage and handling, particularly when it is indoors. Therefore, careful design of the feedstock storage and handling systems, including robust firefighting systems, are required. Other safety concerns with biomass handling include the potential growth of bacteria and fungi on some types of biomass, and the release of VOCs when the biomass is stored, which all present health and safety hazards to any workers in the area. Proper air circulation is therefore extremely important. These safety concerns need to be kept in mind throughout the entire process of the biomass handling system design. All right, moving on to our main presentation. We'll start our presentation today with a discussion of the need for biomass gasification, including the need for waste utilization and renewable fuels. We'll also look at how gasification compares to other processes, give a more in-depth look at types of gasifiers, and end with a look at considerations for the balance of plant design. I'll start with the need for waste utilization and renewable fuels. However, before we get too far into details, I want to define some terms for anyone who is less familiar with gasification technology. Gasification, at the most basic level, is a process which converts carbon-based fuels into a vapor comprised mainly of hydrogen, carbon monoxide, and carbon dioxide. In biomass gasification, the feedstock can be any of a number of types of biomass, including municipal solid waste or MSW, refuse-derived fuels or RDF, wood products, or waste tires. The main vapor product from the gasifier is called synthesis gas, or syngas, and unlike combustion products, retains much of the heating value from the feedstock. Syngas is then further processed and converted into useful products such as heat and power or chemicals, including hydrogen, methanol, and Fischer-Tropsch liquids. Before we get any further into the technical details of gasification and how it works, I want to first discuss why and when it is needed. The ability to utilize waste as a feed for gasification is important given the extremely high waste production rates worldwide. Global annual municipal solid waste production is currently at over 2 billion tons per year and is still growing, with a predicted waste production of 3.4 billion tons per year by 2050. Waste production varies significantly across the world, ranging from about 0.1 to 4.5 kilograms per person per day. Highly urbanized countries generally produce more municipal waste. The map on the left shows a breakdown of the estimated waste generation per person, with countries in orange like the United States, Canada, and Australia having the highest waste production on a per capita basis. In addition to municipal waste generation, other types of waste are also produced in large quantities. For example, industrial waste is at a global average of nearly 13 kilograms per capita per day. Agricultural waste accounts for another 3 kilograms per capita per day, and construction and demolition waste for another 1.7 kilograms per capita per day. All of this waste has to go somewhere, and unfortunately, about 70% worldwide, on average, currently goes to landfills or open dumps. While recycling and composting are becoming more common, they still only account for less than 20% of waste treatment. And let's look at the United States in particular as an example of waste generation. In the United States, total MSW generation, which is shown on the graph on the left, was just under 300 million tons in 2018. Of that, about half was sent to landfills, and the amount to landfills is shown on the right. Many current conservation efforts are focused on increasing recycling and reuse. The increase in recycling is what has allowed the total landfill tonnage to remain fairly stagnant while the total MSW production grows. However, at 150 million tons per year, there is still plenty of waste going to landfills, and there is clearly a need for additional waste utilization beyond recycling. Gasification can help fill this gap. In addition to being a waste of resources, literally, landfill usage is also a concern because the amount of MSW produced in the United States is high enough that some regional landfills are filling up. Because space is often at a premium, other landfills charge a fee, called a tipping fee, to deposit waste there. When other uses, like biomass gasification, are found for the waste, this tipping fee is often available as a revenue stream or saved cost. The other major concern with sending waste to landfills is the resulting emissions. As MSW decomposes, it emits significant amounts of methane, which, on a pound-for-pound basis, has an impact 25 times that of CO2. In 2018, U.S. landfill emissions were equivalent to more than 110 million metric tons of CO2. And to put that in perspective, that's equivalent to the greenhouse gas emissions that would come from 20 million passenger vehicles over just 1 year. This puts MSW emissions in the United States as the third largest source of human-related methane emissions. In addition, as you can see from the map, as you'd likely expect, the most significant landfill emissions are in areas with the highest urbanization. These are also generally the same areas that have other air quality and pollution concerns already. To combat greenhouse gas emissions and pollution, many U.S. states and other countries have enacted limits on CO2 or methane emissions. Many places use a cap-and-trade system, which limits CO2 emissions while effectively putting a value on saved emissions. Utilizing waste as a feed for gasification that is otherwise destined for the landfill may qualify for these or other credits, particularly when carbon capture is employed in addition to gasification. Clearly, biomass gasification is useful because the feed can be waste streams that would otherwise be discarded. On the product side, biomass gasification can also provide significant benefits since the products can be considered green or renewable, depending on the feedstock and plant location. If the product is a fuel, such as hydrogen, Fischer-Tropsch liquids, or even electricity, it can be classified as a renewable fuel. This is valuable for two reasons. It helps meet local renewable energy goals by producing low carbon intensity products, and it helps the project because additional revenue streams in the form of credits are often available. Renewable and green products are particularly valuable in places like California that have high targets for renewable fuel and electricity generation. California has a goal of 60% renewable energy on their grid by 2030 and 100% by 2045. To put that in perspective, currently only about a third of the electricity in California is from renewable energy, about 6% of which is from biomass. On the fuel side, California has announced that all new passenger cars sold in the state should be zero emissions vehicles, such as those run on hydrogen or electricity, by 2035. And although California already has a significant renewable energy infrastructure, there's still a ways to go to meet these targets. Biomass gasification can help be a part of that puzzle. While California's goals are currently more ambitious than those in many other locations, we believe California is at the front of the curve and serves as a model of the future. It's expected that more and more places will follow with renewable energy goals of their own, which will further drive the need for solutions like biomass gasification worldwide. Based on all of these trends, there's a few major scenarios where biomass gasification can be a particularly effective tool. For example, gasification is beneficial where there are large quantities of biomass available. This might be near a landfill, and as previously mentioned, if the landfill has tipping fees available for diverted waste, the economics of the project can be further improved. Areas with other sources of biomass should also be considered, such as in a region with a lot of agricultural waste or near a forest with forest floor cleanup required. Transportation costs must also be considered. Due to the relatively low energy density of biomass, transporting biomass feedstocks over long distances can quickly become cost prohibitive. So the location of the gasification plant is important. And as previously discussed, biomass gasification can be a good solution in areas where producing hydrogen or other fuels with low carbon intensity is particularly important. Let's take a quick look at the carbon intensity of hydrogen production to see how biomass gasification compares with other methods of production. Carbon intensity is calculated by considering all greenhouse gas emissions from the fuel production process, including feedstock emissions and end-use emissions. It also considers saved emissions from the feedstock's original purpose. Carbon intensity is reported on the basis of grams CO2 equivalent per megajoule of fuel. Hydrogen produced via traditional steam methane reforming has a carbon intensity of about 120. Hydrogen produced with electrolysis using the average California 2020 grid electricity has a carbon intensity of about 147. Hydrogen produced via electrolysis from wind or solar power has a much lower carbon intensity, around 11. Hydrogen produced from biomass gasification without carbon capture falls somewhere in between, with a carbon intensity of around 45. When carbon capture is added, the carbon intensity with biomass gasification can drop below zero, since there is now a net reduction in emissions to the atmosphere, for example, by reducing the landfill emissions. Note that the actual carbon intensity can vary significantly based on the type of biomass and plant configuration. Having a low carbon intensity product is always desirable, but it can also particularly benefit the project when it aids in qualification for any renewable fuel credits that are available in the area. I'd now like to return to a description of the biomass gasification process and look at how it works and what it can be used for in a little more detail. Although biomass gasification is a quickly expanding area, gasification in general has been around for a century and is frequently used with coal and petcoke as feedstocks. As I mentioned at the start of the presentation, gasification converts solid fuels to syngas. The process can be broken down to three major, often overlapping steps: drying and preheating, pyrolysis, or the decomposition of the feedstock, and the gasification step, with heat often provided by combustion. The gasifier itself generally operates at high temperatures and above atmospheric pressures. An oxidant such as oxygen or air and/or steam is also required. The major reactions are shown on the slide and include combustion and carbon conversion, boudoir, water gas shift, methanation, and reforming reactions. These reactions convert the carbon and other components from the feedstock and the oxidant fed to the gasifier into the hydrogen, carbon monoxide, carbon dioxide, and methane that is found in the syngas. While I've mainly discussed MSW as a feed so far, biomass gasification can utilize a variety of sources as the feedstock. Biomass is divided into two main categories, primary biomass and secondary biomass. Primary biomass includes things like forest biomass, agricultural crops, and plant residues. Forest biomass in particular can be a great feed for biomass gasification in areas like California that have a high focus on forest residue removal as a method of fire prevention. Secondary biomass comes from conversion of other organic material. MSW falls into this category, as does demolition wood, food waste, and sludge and sewage, all of which can be considered for gasification. On the product side, a wide range of chemicals and fuels can be considered based on what is most advantageous at the time for the specific plant. Syngas can be directly used to produce heat in the form of hot water, steam, or electricity. It can alternatively be further processed to make Fischer-Tropsch liquids, which includes naphtha, diesel, jet fuel, and wax, or other chemicals such as hydrogen, synthetic natural gas or SNG, methanol, ammonia, or other chemicals. In addition, gasification plants often have other byproducts which can be sold, including argon, nitrogen, and oxygen from the air separation unit, carbon dioxide, and sulfur or sulfuric acid. Many gasification plants will produce more than one of these products. Syngas is an advantageous product precisely because it can be used for so many end products, and the plant configuration can be selected based on what is most needed or most profitable. So let's look at the relative prices of some of these products. These tables show representative examples of the price of feedstocks and products in the United States. The first message from these prices is that there is a clear difference in the potential revenue from different products. Prices can also vary, sometimes widely, over time and based on the plant location. Therefore, it is important to do a thorough evaluation to choose the best product for the facility. This evaluation should include a market study along with a consideration of the efficiency of getting to each product. The second message from these tables is how gasification is a value-added process with a large increase in the dollar per million BTU value of the products compared to the feedstock. If you're familiar with biomass conversion processes other than gasification, you might have noticed that many of the gasification features I've discussed overlap with other processes. I'll now explain how gasification differs. One of the more common usages for biomass is to combust it in a power plant. Although several of the reactions are overlapping, gasification differs from combustion in several key ways, and therefore has different uses. The products of gasification retain their heating value, unlike combustion. For example, in gasification, carbon is mostly converted to carbon monoxide instead of carbon dioxide in combustion. Hydrogen is primarily converted to H2 instead of water, and so on. Because biomass gasification retains the useful heating value of the feedstock, it can therefore be used to produce fuels and products other than power. There is also no excess oxygen in gasification, unlike combustion. Other common biomass treatment processes are drying, torrefaction, and pyrolysis. You can see here a high-level comparison of gasification to these processes. Drying takes place at the lowest temperature and removes some of the surface moisture of the biomass. Torrefaction occurs around 350 to 600 degrees Fahrenheit and produces a torrefied biomass with a higher carbon content and lower moisture content. Pyrolysis can occur anywhere from about 550 to 1100 degrees Fahrenheit, and depending on the temperature and the speed of pyrolysis, produces bio-oil, charcoal, and some gas. Gasification takes place at the highest temperatures of any of these processes besides combustion, and is the only one to produce syngas as the main product. I'll now hand it over to Sanjiv to talk about types of gasifiers.
Thank you, Katie. Now that you guys are all familiar with the various terminologies of biomass and gasification, I would like to walk you through some of the gasifier types. So the first type, the moving bed, also known as a fixed bed gasifiers, has been here for a very long time. Actually, these gasifiers were used in the 1800s. A moving bed gasifier is characterized by a bed in which the solid feed moves slowly downward under gravity as it is gasified. The next one, end-train flow gasifier, is the most successful and widely used type of gasifier for large-scale gasification. The feed can be liquid or a slurry of solid and liquid fuels. The next one, the fluidized bed gasifier. It is based on the fundamental principle of fluidization. In such a gasifier, the fuel, together with the inert bed material, behaves like a fluid. And lastly, the plasma gasifiers. In a plasma gasifier, an electric arc is used to create a plasma. The feedstock can be any material with carbon source and is gasified at very high temperatures. So before I take a deep dive into the various types of gasifiers, let us look at the differences in the properties of biomass versus traditional gasifier feedstock. As one can see in this table, biomass is very low energy feedstock, with typical heating value of around 4,000 to 8,000 BTU per pound, as compared to coal, which typically have anything from 13,000 to 15,000 BTU per pound. So one need to process a lot more tonnage of biomass feedstock for the same equivalent syngas production. Biomass can also have very high moisture content, anything from 10 to 68%, whereas it is more common to see 5 to 12% in a typical coal. Typical moisture content for gasification feed is around 10 to 15%. So as you can see, if you have a biomass feedstock, it is often required to have a drying step before it is fed to the gasifier. Although the table shows very low ash content for the biomass, ash content for some biomass feed, such as straws and husk, can be much higher, even up to 15 to 20%. Sulfur content tend to be very low for biomass compared to coal or pet coke. Other component that one is typically interested in defining a gasification feedstock is chloride. So the chlorine can vary depending on the source of the feedstock, and it also can vary seasonally. For example, your household lawn clipping that you put in your recycle bin can contain a lot more chlorine in summer due to irrigation. Okay, so let's get back to the working of the various gasifiers. In the moving bed gasifiers, the solid feed moves slowly downward in the gravity as it is gasified, and the syngas generated moves in a countercurrent to the feed. In such a countercurrent arrangement, the hot syngas from the gasification zone is used to preheat and powderize the downward flowing solids. Pyrolysis, char gasification, combustion, and ash melting occur sequentially. This arrangement reduces the oxygen consumption. The outlet temperature of the syngas is generally low, anything between 850 to 1200, I'll say, although higher temperatures are reached in the heart of the bed itself. As a result of the low syngas outlet temperature, a relatively large amount of methane and tars are produced. Moving bed processes operate on a lump material. If an excessive amount of fines is present in the feed, it tends to be entrained with exiting syngas and can block the syngas flow paths. So example of moving bed are Logie dry bottom gasifier and British gas Logie slagging gasifiers. So the next one, end-train flow gasifier. It is the most successful and widely used type of gasifier for large-scale gasification. The feed can be liquid or a slurry of solid and liquid fuels. They are injected through a burner or a mixer together with oxygen as a gasification agent. The gasification temperatures are between 2200 to 2900 degrees F, and the operation can be anything from atmospheric pressure to over 1,000 pounds. The residence time of these gasifiers are very short, usually only a few seconds. With high operational temperature, tar production is minimized. The short residence time can also be a disadvantage, as it requires very fine grinding of the feed. Now, grinding fibrous biomass into such fine particles is very difficult. Additionally, entrained flow gasifier need ash to be molten. For biomass with high calcium and low alkali metals, such as sodium or potassium, the ash melting point is high, and therefore to provide for such high combustion temperature, a high amount of oxygen is required. Molten biomass ash is also very aggressive, which greatly shortens the life of the gasifier's refractory lining. For this reason, entrained flow gas reactors are not preferred for biomass gasification. So example of entrained flow gasifiers are G, E-gas, MHI, Shell, and ECAS. So the next one I want to talk about is the fluidized gasifier. It is based on the fundamental principle of fluidization. In such a gasifier, the fuel together with an inert bed material behaves like a fluid. This behavior is obtained by forcing a gas, the fluidization medium, through the solid inventory of the reactor. Air, steam, or steam and oxygen mixtures are examples of commonly used fluidization media. Silica sand is the most commonly used as a bed material. Circulating fluidized beds operate at high gas velocities, typically anything from 9 to 30 feet per second, dragging the solid particle upwards with the gas flow. These particles are separated from the gas in the cyclone and recycled back to the bottom of the fluidized bed. Because fluidized bed gasifiers would plug if ash were to melt, the bed temperature must be below the ash melting or slagging temperature. Hence, the maximum operating temperature is limited by the melting point of the bed material, and typically lie between anything from 1400 to 1800 degrees F. These gasifiers have a better tolerance for fines and have a very high coal gas efficiency. They also have a very long residence time, which make them a good candidate for biomass. As in any fluidized bed, the particle size of the feed is very important, and therefore, sizing of your feedstock is paramount. Example of CFB gasifiers are the GTIU gas gasifier, the low-key circulating fluidized bed, and Ripotec twin reactors. So the next one is the plasma gasifier. Plasma is just very high temperature thermal energy. It is sometimes referred to as the fourth state of matter. Possess the commonly known phases that everybody is familiar with: solid, liquid, and gas. In a plasma gasifier, an electric arc is used to create plasma. The temperature of up to 9,000 degrees F is created at the torch. The high temperature experienced in a plasma gasifier of up to 5,500 degrees F ensures complete destruction of the feedstock and allows for the processing of high moisture feedstock, or even feedstock that contain very high level of inert materials like glass and metals. It is insensitive to quality of feedstock due to the high temperature. Therefore, very little pre-processing of the feedstock is required. The syngas exits the gasifier at around 1800 degrees F. The higher temperatures inside the plasma gasifier result in the complete destruction of tars and have very negligible methane in the syngas. The inorganic components of your feedstock, like glass, metal, and concrete, are melted inside the reactor and flow out of the bottom as a non-toxic vitrified molten slag, which can be used safely as aggregate. The slag flows out of the gasifier up to 3000 degrees F and typically are removed by quenching with water. Of course, the aggressive temperature requires high electricity usage and reduces the material life. Plasma gasifier is very well suited for MSW and any solid waste, including hazardous waste. Typical example of plasma gasifiers are the Solina gasifiers and the Westinghouse Alt Energy one. So, in summary, looking at the various types of gasifiers, one can see that the fluidized bed and the plasma gasifiers are the most suitable for your biomass gasification. Of course, there are some variations to these four main types of gasifiers, and one can use a combination of them in developing a plant for yourself. Of note is that these technologies have been out there for a while and will not necessarily be considered first of a kind when developing a project. This also comes up very often when we dealing with client and screening, because if you're building a first of a kind, financing is always a big issue. So next, I want to look at I want to walk you through what a typical plant configuration looks like. So in addition to the gasifier itself, a biomass gasification plant needs to have a significant number of supporting units and infrastructure. The diagram on the screen shows a potential configuration for a biomass gasification plant for hydrogen production with carbon capture. The flow sheet is typically customized based on the feedstock, technology, and final products. The front end of the plant will typically have a feed receiving, storage, and transfer units. Depending on the type of feedstock and gasifier selected, it may also include a sorting, screening, grinding, and drying steps. As discussed earlier on, the gasifier being used has a big influence on the type of feed preparation required at the front end. Next, to support the gasification process, the plant will typically have an air separation unit, or ASU. Depending on the size, it can be either a cryogenic unit or a VPSA. So the VPSA is just a vacuum pressure swing absorption. We have discussed the gasifier itself early on, but irrespective of the selection, it will have a slag and ash handling system. Typically, the slag or ash are sent for disposal offsite. As discussed earlier, the syngas leave the gasifier at very high temperatures. So the syngas is cooled by generating various levels of steam and then scrubbed to remove any particles, came over, and trace components such as chloride. The steam generated is used to make power, while the condensate is sent for further treatment. The cool scrubbed syngas is then compressed and sent to a shift unit, where all the CO is converted to hydrogen and CO2 via our water gas shift reaction. The shifted syngas is then sent to an AGR. The acid gas removal unit then removes the acid gases such as H2S, cyanide, and CO2. The CO2 can then be compressed and sent to a pipeline for EOR or sequestration, depending on where your location is. The H2S is then sent to a sulfur treating plant, such as a typical SRU, or if it's a small plant, a low-cat unit, depending on the amount of sulfur in your feedstock. So finally, the hydrogen-rich syngas is then sent to a pressure swing absorption to produce very high purity hydrogen. The pure hydrogen is then compressed and sent to pipeline. So from the hydrogen unit, you always have a tail gas. This can be used as fuel gas for the plant. So the above configuration is typically defined during a screening study for the client, depending on their feedstock, their product, their location, and also their business drivers. So more utilities are needed compared to any other green methods of hydrogen production, such as electrolysis. For the folks in the audience that are familiar with oil, gas, and petrochemical plant, these are very common. So to start with, these plants will have, feed, product, intermediate, chemical storages. So that can take quite a big portion of your OSBLs. And to support all your processing that you have, your cooling and everything, you'll need a cooling water system. Now, the cooling water system itself, you'll have to get a raw water treatment, and all your other water leaving the plant will have to go to wastewater treatment. So that has to be defined. And to support the steam that you're going to make power, you need a dimming water system. And of course, the steam itself will have a whole steam and condensate system unit as you're making the steam. And to supply all your equipment and instrumentation, you'll have a plant instrument air system. and such thing as nitrogen for your purging, for your startup, and all your other activities. And as any of these plant, you always see a big flare to make sure that you can have emergency and start up and shut down safely. The plant itself always have some sort of backup power with a full electrical grid. And finally, as any of these big plants, so you have to consider the buildings such as control room, mechanical maintenance, warehouse, and all your communications there. So quite a infrastructure behind it, again, compared to your electrolysis, but nothing new if you are in the oil and gas business. So in developing the flow sheet for a biomass gasification plant, one needs to be aware of the various design considerations. So understanding the challenges associated with biomass is critical. The morphology of the feedstock is important in defining the feedstock preparations such as grinding, drying, and feeding. Syngas cleanup depends on the final product one is targeting. For example, if you're just making power, it requires much less cleaning versus if you're making chemical, which typically have very sensitive catalysts that can get very easily poisoned by any trace components or contaminant. One needs to also have a very deep understanding of the chemistry for modeling the whole process. This is important so that your design can make sure you cater for all upset conditions and also sizing of all your equipment, including material selection. And remember, knowing those components also help you to define the balance of plant. Biomass with high alkali content need to be carefully analyzed as the ash could increase plugging and have excessive wear and tear on the refractory. Tars, like I discussed earlier on, depending on the gasifiers you're using, can cause a lot of fouling of your equipment and should be handled accordingly in the design. Chlorides and other trace components have to be characterized as they often dictate the metallurgy of your equipment. There is a saying in our business that says, don't worry too much about the 99% of your feedstock, but be very aware of the 1% of your feedstock. We would typically do a screening study for a potential client to address all these parameters to take into consideration of their OPEX, CAPEX requirement in developing the flow sheeting. I will now pass it back to Katie to further discuss some of the other design considerations we'll look at.
Thank you, Sanjiv. Other miscellaneous considerations include the high gasifier operating temperature, which can require the use of refractory and can also lead to problems such as high temperature hydrogen attack or chloride stress corrosion cracking. Metallurgy must be carefully selected, taking into account the range of expected operating conditions, plus the composition of the syngas and the biomass. Regional biomass availability should also be considered, including, as previously mentioned, the transportation and collection costs, as these can be quite significant. There are also some operational considerations to be aware of. Gasifiers typically require periodic maintenance. For example, the refractory of the gasifier has a limited life and will need to be inspected and replaced. In plasma gasification, the life of the torch will need to be evaluated. Maintenance requirements should be discussed with the gasification licensor, and for large plants that require high availability, we may want to consider spare gasifier trains. Another consideration is the oxygen usage. As Sanjiv mentioned, oxygen-blown gasifiers require significant amounts of generally very high purity oxygen. To make oxygen at the purity required, a cryogenic air separation unit, or ASU, is generally needed. ASUs are expensive and need to be fairly large to take advantage of economies of scale. They also have a significant operating cost due to the power required to operate the compressors in the unit. This electric power also correlates to an increased carbon footprint for the unit and consequently the plant. To avoid using an ASU, vacuum pressure swing absorption, or VPSA, units can be considered instead, although the oxygen produced will be at a lower purity. Alternatively, air-blown gasifiers can be used. However, with this configuration, the nitrogen in the air ends up in the syngas, diluting the heating value. If the syngas is used for anything other than power production, significantly more treatment is required to remove the nitrogen. Another unit which requires careful design thought is the feed preparation and handling unit. A high level of biomass pre-processing is required, due in part to the high moisture content and the fibrous structure of the biomass. The exact pre-processing configuration will depend on the type of biomass used and the specific gasifier requirements. However, in general, the steps required are unloading, where biomass is often transported via truck to the site and then must be unloaded. Screening, to remove any metals or other unwanted materials. Storage, and due to the low density of biomass, storage can take up quite a significant amount of space. Feed preparation, including sizing and drying. The exact specifications will depend on the gasifier type, and Sanjiv mentioned some of the typical requirements for each type. Intermediate storage of sized and dried biomass to increase the availability. Conveying from one step to the next, and then finally feeding to the gasifier. The type of feeding system must be carefully considered since gasifier normally operates at pressure. Types of feeding systems include belt, chute, rotary, screw, and gravity feeders, or pneumatic injection. Feedstock variability across the seasons also needs to be considered in the design. Depending what biomass is used, there can be large swings in the biomass composition, which will lead to changes in the gasifier operation and syngas product. All of these considerations need to be kept in mind from the early stages of the project development to ensure that the plant is safe, efficient, and well designed. There's a growing awareness today of the need for environmental responsibility, both on a personal and a corporate level. Many major companies are supporting reduced carbon emissions, waste reduction, and other green initiatives. We have seen similar trends on a political level, with incentives offered for green fuels and power and lower greenhouse gas emissions. Biomass gasification can help meet these goals, and with waste and other feedstocks readily available in many areas, it is an opportune time to do so. Gasification is also a favorable option since it is a well-proven technology, unlike many other green alternatives. All of these factors support what we expect to be an expanding market for biomass gasification in the coming years. Thank you.
Thanks, Sanjiv and Katie. I'd now like to open it up to questions from our audience. Please make use of the Q&A tab to ask any questions and be sure to address your questions to all panelists. We've received a few questions here. I'll go through. First one is Sanjiv. How do the capital and operating expenses compare for the various types of gasifiers?
That's a good one. So the exact capital cost will vary based on the plant location, the scale of the plant itself, and of course the feedstock type that I've mentioned many times in the presentation, and of course the product itself. In general, entrained flow gasifiers tend to be somewhat more expensive than the fixed bed or fluidized bed. That's because they have a larger oxygen requirement and also a higher feed pre-processing requirement, right? So the plant scale itself makes a big difference. And if you look at plasma gasifiers, it often comes in small train sizes, which means they don't have much as economy of scale as you would think with the large gasifiers. This makes them good for smaller plants, but other gasifier types may be more suitable if a large scale plant is needed. Operating costs also vary depending on the location and the plant configuration. So again, it has so many variables, so it's very difficult to just give one answer. So on the operating costs, for example, one big one is the electricity, right? So if you have a big ASU, it consumes a lot of electricity for the MAC and the BACs. Those are the main air and boost air compressor. And that has to be factored in your flow sheeting. And if you have like a plasma gasifier, the plasma gasifiers run at pretty much atmospheric conditions just above that. So that means you'll have a big compression portion of it to process the chemicals into whatever product you want to make. So that will be another portion of the cost. And at the same time, plasma gasifiers, like I mentioned before, it operates at very high temperature because of the arc and the plasma that you create. So now you have to include the electricity cost of that and also the wear and tear. So if you have multiple trains, you have to put that in your overall capital cost. So because of the sparing philosophy. So again, not having a straight answer for you guys, but it varies on a lot of things. And but you know, again, if somebody come to us with you know, a business model that they have in their mind, we can help them by looking at, you know, where the location is, what the products make, and then we tend to choose which one will fit their business models, which type of gasifiers and which type of flow sheeting you're going to do. We at Fluor, we tend to be typically technology agnostic, so that we work with all the different licenses. So we'll build a flow sheet to basically meet the client needs rather than just one technology. Katie, anything else to add on this?
No, nothing else to add, Sanjiv.
Okay, thank you. The next question I'll direct to Katie, and this is pertains to slide 33. How do downstream units differ with different types of gasifiers?
Sure, so that's a good question. So on slide 33, we've showed a typical plant configuration for hydrogen production. But there's a few different operating parameters that different gasifiers have that will affect the downstream units. So if you look at the pressure of the gasifier, that will affect that syngas compression step there. So some of the gasifiers, the plasma gasifier in particular, operates at a near atmospheric pressure, which means that there's more syngas compression needed compared to higher pressure gasifiers like the fluidized bed gasifier. And then it's just important to keep in mind that the amount of syngas compression needed, it'll also depend on what you're making, because different downstream units will require different operating pressures. If you look at the gasifier type, there's also some differences in composition. So one of the key differences there will be the amount of methane content that's in the syngas. So Sanjiv talked a little bit about how it differs for the different gasifier types. So if you have a syngas with higher methane content, that's not particularly beneficial for a flow sheet like this with hydrogen production. But it would be very beneficial if you're trying to make, say, power or SNG instead. And another difference between the gasifiers would be the tar production. So gasifiers that destroy a lot of the tars, again, like plasma gasification, don't need the downstream tar cleanup processes compared to some of the other ones. And then beyond gasifier type, we talked a little bit about how these units will differ based on products. So we'll need a shift unit no matter what, if you're making hydrogen or other chemicals in general, and then the amount of purification needed will matter depending on what product you're making. And then just one other thing to mention with this flow sheet here is the air separation unit. We talked a little bit about using air instead of oxygen. And if you do that, you'll save on operating expenses, the ASU operating cost, the oxygen production cost. But you'll need larger downstream units. So you're basically trading OPEX there for CAPEX. Sanjiv, anything to add?
Yeah, I think you covered it all. And again, the point there is, you know, lots of people, if they use air-blown gasifiers, and that's quite a few plants if you're making power. But remember, you know, air is 79% nitrogen. So to meet your same oxygen requirement for your gasification, you're basically putting almost 3 times the volume. So like Katie said, now suddenly you need to process that amount of volume in all your downstream units so that you're making all that pots and pans much larger.
Okay, thank you. The next question I'll direct to Sanjiv. Can Fluor share any biomass gasification projects that they are currently executing? What is Fluor's role in these projects?
So we are involved with a number of biomass gasification projects, especially in this transition economy. But unfortunately, most of this client, you know, as you think, is trying to get the fastest to the market. So a lot of them are confidential, but I think people can see some of whatever has been announced in the public media. But I would just say, yeah, we're working on a number of them, but I can't disclose any of them.
Okay, thank you. The next one I'll direct to Katie. What is the rough capacity of a typical biomass plant? Presumably, these are small scale facilities.
Yeah, good question. So these are often smaller in scale compared to your typical coal or petcoke gasification plants. So if you're looking at a single train of a biomass gasifier, it depends again what type of gasifier type you're looking at, but it would be anywhere from, I'll say maybe 100 tons to 1,000 tons per day of feedstock. And then, of course, if you are looking for a larger scale than that for whatever you want your product rates to be, you can combine multiple trains of gasifiers together.
Okay, thank you. The next question we have, I'll direct to Sanjiv and or Katie. What standards would you refer to while designing a biomass gasification facility, especially for emissions and for flare design?
So, I mean, again, like I discussed early on with the flow sheeting, so your biomass gasification will fall typically under, it's more like a petrochemical complex rather than, an electrolysis. So, whatever standard you apply, whether the API or for flare, like 521 and things like that, that you apply for a oil and gas facilities, it will be very similar. And again, remember, I keep hopping on that. It's also on your location, right? So for example, when we build a plant in California, we have much stricter air emissions, water, anything is much stricter here versus other places. I mean, that just within the US itself, it varies from state to state. So the same thing if it's in Europe or other part of the world, you'll have to meet those local regulations. But a simple answer, I would just say your normal, typical petrochemical or oil and gas standards will apply.
And I would just add on to that, one of the things that should be done early on the project is looking at the permitting process. And again, that's pretty location dependent, but that'll take into account what you were talking about, Sanjeev, with you'll look at the country regulations for emissions, if there are any state ones, and then, even local city or in California county regulations would be considered at that part of the process as well. That's a key step.
Okay, thank you. The next question that we received, I'll direct to Sanjiv. Are there any reliability or operational issues with the syngas cooler used in biomass gasification?
Yeah, it's for people who are familiar with gasifiers, I mean, uh, you know, gasifier is very different to many like, straight heat exchangers because you're handling solids and slurries, and when you're gasping at that high temperature, you have ash moving around and you have those deposits. So it's a problem across the whole industry, whether it's biomass or just generally trading coal or petcoke. So it's very important that one look at all the cases and include that in your design, and that's a big part of once somebody moving from a screening study to a full feed, to make sure those um, considerations are included in the design. And that's why it's important that if you're choosing a technology, that you choose a technology that has demonstrated that the technology is viable, have a lot of operating experience, because sometimes that's why I mentioned that point of first of a kind. If you try to build these things and theoretically you can just say, oh, this is not going to happen, but when you're running the plant, you have all these problems. So it's important when you're choosing a technology that has already plant running, and you basically try to get those lesson learned incorporated in your design. But ash, especially with biomass, like I mentioned early on, with is if you have those potassium or sodium or any of those uh, alkali metals, it can provide lots of headache. But lots of the like the plasma gasifiers, there's many examples of lesson learned when they build the first pilot plant to the commercial plant, and then as more and more of those plant has been built, the lesson learned has been incorporated in the design.
Thank you, Sanjeev. The next question I'll direct to Katie. Why is drying of the feedstock required given that the gasifiers operate at high temperature and steam is required for some of the gasification reaction?
Sure, good question. So basically, if you don't dry the feedstock, it requires more energy to heat up and evaporate the water that's part of the feedstock there. So it's basically pre-drying the feedstock is a way to increase the efficiency of the gasifier itself, decrease the amount of heat that's not going towards the process and is just going towards water evaporation, and then decrease the oxygen usage as well with pre-drying the feedstock. So it's all just an efficiency comparison.
Yeah, I would just add to that. Just remember, the water itself is taking a free ride, right? So you're changing it from liquid to vapor, which happens just at, very low temperature. But then anything from 100 degrees C all the way to the thousand of degrees, that water is being superheated. And so where is that energy coming from? So if you have oxygen, so you basically some of the combustion that's taking place is providing that energy, right? Like Katie said, at the end of the day, so you're losing efficiency that way.
All right, thank you. Again, I'll direct this one to Katie. Is gasification a good option for production of renewable natural gas?
It can be. It depends on, again, we talked a little bit about the product prices, and your plant location, and it's mainly going to be an economics driven trade-off. So you want to look at what you can get for renewable natural gas in the area. Again, if there's any credits available for producing basically a green power source, compared to what sort of price you'll need to pay for the incoming biomass. Again, if it's a waste and you've got a tipping fee, that tends to make all of the projects look much better than if you have to pay for your feed source. So it's something we would look at as part of that initial screening study that we've mentioned a few times.
Okay, thank you. It looks like that is about all the time we have left for questions. Thank you, Katie and Sanjiv. To our audience, we appreciate your attending and for your engagement today. It's been a pleasure being your moderator. Please continue to stay informed of these events by visiting the Innovation Builders page on fluor.com or following our social media channels using hashtag Innovation Builders. If you'd like us to send you email notifications of future webinars, please email us at innovation.builders@fluor.com with opt-in in capitals letters in the subject line. We appreciate your attention and thank you again for dialing in today. We will send out a compiled list of the Q&A within a few days. Expect to see the webinar recording available on demand mid-next week at fluor.com. If you have any questions or require additional information, please email innovation.builders@fluor.com and someone from our team will get back to you. From all of us in the Innovation Builders team, have a safe day.